Hi everyone, I'm Roger. Welcome to Data Club. This is a bi-weekly meeting at Columbia that is dedicated to mostly Python, but also some non-Python related computational plus data libraries and ways of working with data with computers. So the way this is going to work this year is that we are going to have an hour-and-a-half meeting every 2 weeks, and that will be, say, about an hour worth of content, and then the rest of the time for questions or working through whatever we like. And we're kicking off the year with a library that, as a scientist, I think is cutting edge and fundamental, Xarray, which is a library that allows you to work with n-dimensional data sets, which for science is crucial. So we're going to work through this Jupyter collab, this Google collab, and hopefully find our way to some understanding. This is about you. This is about you learning. It's not about me going through the material at any particular pace. So I would much rather us not get through all or most of this material and have you both understand what's going on, rather than us like speed through and then say, oh wow, we did it. That's not useful. Okay, so we're going to start with some fundamentals of what Xarray is and what it does. And as I said, Xarray is an excellent library for working with tabular labeled data that can be in 2 dimensions, but also can be in n dimensions. For instance, in my science world, you might deal with a temperature data set that's latitude, longitude, and time. So you're a satellite and you're measuring Earth's temperature, and you take a data set that's 2-dimensional every hour. And when we say the data set is labeled, we mean that each of the variables has metadata associated with it. So it's not just numbers, it's numbers that have words describing what they are. This graphic, I think, is kind of helpful for understanding how Xarray works. And the data structures, we're going to be talking about data structures a lot, because when you start to get multiple dimensions, you have to come up with a way of keeping track of which dimensions refer to what kind of data. So if you just have a blank array and it's your temperature array and you don't have anything attached to it, then you have to remember that latitude is the first dimension and longitude is the second dimension. And if you get that mixed up, then all of a sudden you have a bug in your code. So one of the reasons that Xarray was developed in the first place is to prevent that from happening. So it's the fundamental variables here are the fundamental units that make up Xarray is you have a bunch of different variables. You have coordinates associated with those variables. You have dimensions. And then variables, coordinates, and dimensions get wrapped in these data structures called a data array data set. So basically, you have the temperature data. You then have the coordinates that are associated with it, with latitude and longitude. And then you have dimensions. So for instance, say latitude and longitude, if you're measuring in an XY grid, are not just equal because it's on a sphere. So latitude and longitude might have an x and y coordinates in space, in like meters away from the pole or something. So the dimensions would be x, y, and time, and then latitude would have x, y, and longitude would have x, y. Okay. So we have data sets, data arrays. The core attributes of a data array are the values, the temperature, the dimensions for each axis, the coordinates associated with each point, and attributes. So attributes could be the name of the satellite that produced the data. It could be the computer that you use to post-process the data, just like things that you want associated with the data, but that don't actually bear on the data itself. Yeah?
So about the coordinates, I'm a little bit confused just because that's not latitude and longitude. What's the relationship between latitude and longitude in the picture that you showed and the idea of the dict-like container of arrays that is coordinates? Or will you get to that?
I will get to that.
Okay.
It may be helpful to look at an example. So let's get there, and then let's see if that can be helpful. Okay, so the way that Google Colab works is that you have these series of cells, and I'm just imagining that we're starting from the beginning. And forgive me if I'm telling you things you already know. Perfect. Okay. So the way Google Colab works is you have a series of cells, and each cell can be run. So when you run a cell, whatever is in the cell, you're telling the computer, do this. And in our case, Google has a computer somewhere that's connected to your notebook. So there's a virtual machine somewhere, and you're saying, OK, do these commands. And the way you run a notebook is you press the little play button. So what we're doing first is we are importing some libraries. You can think of a library. If you're in a kitchen, a library is like an ingredient. You're pulling different ingredients off the shelves. You're going to cook something, but you have to have, is that a good analogy? Kind of. You need, or maybe it's like recipe books. You're taking the different recipe books down. NumPy, not NumPy, NumPy is the basic linear algebra computing library for Python. So if you need to do interpolation, if you need to do most numerical computations, there is a function like cosine. There's a function in NumPy that you can call upon and use. Just like if you had a graphing calculator, you would say cosine of 60. Similarly, you could invoke NumPy and use the cosine function. So when we say import NumPy as NP, what we're doing is bringing that library into our little system. Same thing with Xarray. Matplotlib is the plotting library. Great. OK. So we're going to start off the simplest. We're going to say, let's make a little function, f of x equals sine of x. So we're saying x equals, let's make an array from negative pi to pi, and let's have it be 19 numbers long. And then let's take the sign of that array. And if we look at f. So we're going to run that. We have this array of numbers that is the sign, that is signed from negative pi to pi. Okay, so first, we're going to say dA underscore f equals xarray.data array of f. And then let's look at it. So when you run a cell and you have a variable as the final line, it prints out whatever is in the variable. So we've just made this vanilla array, data array. That's going to think about it for a second. Cell is already running. Great.
Can you quickly describe that linspace
Sure.
method?
Yeah, for sure. So up here, NumPy has this function called linspace, and we could look at what it takes in, but basically it takes in a start value, an end value, and the number of values in between, and then creates an array that has linearly spaced numbers between those two values. So we said start with negative pi, go to pi, and have there be 19 equally spaced numbers between. Yeah, good question. So, okay, so this ran, and we see we have this Xarray data array. It has dimension 0, and there's 19 of that dimension, and within it, it has this array, because all we did was wrap this array with Xarray data array. That's it. Okay, so that's not all that exciting, but let's just copy this, copy, and put it here again, and let's add something. Let's say dims equals x. And let's run that and see what it looks like. So now, whereas before we had dim 0, it's default. Now, we've labeled this dimension as x. So now it knows that x, that this data array has one dimension and it's x. Let's copy this once more. And add a coordinate. So now we're going to say chords equals, and then open bracket, which is Python's dictionary. This is a ton of information to be throwing out. So know that when I arrived at grad school, I was like you. I had never done any coding at all. And I walked into a class where people were saying things like this, and it was like absolute gobbledygook. I had no idea what was going on. So you just kind of retain whatever you can retain, and slowly pick things up, and eventually you'll be a hacker. Anyway, so these brackets indicate a dictionary. And a dictionary actually is what it sounds like, which is the digital equivalent of a book where you go and find an entry and then it tells you something. So here here's the entry, flip through the pages, x, and we're saying this entry x is associated with the variable x. So let's run this. Now we've given it dimensions and coordinates. And so now it has coordinates of x. So what we've said is we have this array that is the numbers of pi, that is pi, or that is the sign of pi, the values of the sign of pi. That's our array. And the coordinates for x are, for this data array, are the values of x, which was the NumPy linspace that we used before. Yes.
How does it know what x is in the coordinates when you define the? Did you define x somewhere and I just missed it?
I did define x.
Oh, when you
up here.
Okay, so that's the lin.
That's the linspace.
Okay, so you're adding. So that's why the x at the bottom, if you scroll down.
Yep.
Sorry, that's why that actually goes from negative pi to pi. So
Correct.
your f goes between. Basically 0 to 0.
0, exactly.
Your this will go between negative pi and pi. Got it.
Exactly.
All right.
Yep. And let's plot that out. I think the next thing I'm going to do is plot it out. Not quite, but we will plot it out in a second. Xarray has a whole bunch of, when you create an Xarray data array, there's a bunch of stuff under the hood, and it's created by creating a coordinate, you've created an index. So we can say, here's our data array, indexes, don't know why it's not indices, and that's the index. It's a pandas index, which doesn't have to mean anything, but it also has a data type and a name. So this coordinate, because we named it x, Xarray figured out that the numbers in this array had a certain data type. Data type is like an integer versus a float. An integer is just like 1, 2, 3, 4, 5, 6, 7. A float is like 1.1, 2.2. A string is like A, B, C, D, E. So Xarray has figured out that it has this data type float. And let's plot it out. daf.plot, and we're going to say marker equals an O. I'm going to run this and show you. When we say plot, we're saying, OK, make a plot of the data in this data array, and the marker is, do we want dots? Do we want x's? We could say marker equals x. And
just for the visualization.
yeah, just for the visualization, exactly.
And so if I understood correctly, so we had like an array of x points.
Yes.
Then we somehow came up with coordinates with like y-axis. Is that?
Yeah, exactly. So the y-axis is the values.
Yeah. How did we come up with those values?
The values came from, we said the coordinates are this, and then
Okay.
let's take the sign of the coordinate. And so Xarray knows, if right now we only have one axis. We don't have two axes. We just have x. So it puts the coordinates, it puts the values on the y-axis. Excellent questions. OK, so with this data array, we can do a bunch of things, like we can say we only want the 10th item. And I've lost my little. So we had 19 values. We want number 10. We could also say, while that's running, daf, we want all the values up until the 10th value. So yeah, so there's the 10th value, 0.34, and it's right there. We could say we want all the values up until the 10th one. That's what that little colon means. And you could say we want from the 5th to the 10th one, for instance, if you wanted to. But this requires that you know what the indices are just in your head of everything, and it might be the case that you don't. So Xarray recognizes that and says da underscore f dot cell dot select x equals 0. So let's select the value where x equals 0. And you could say where x equals 0.2, we don't have a value where x equals 0.2, so this should break. Hopefully it should break. Yep, great. So it breaks, and it gives us an error and says, key error, there is no 0.2. So what we could do is say method equals nearest. And then it would say whatever the closest value is to 0.2, choose that one. OK, great. So this selecting method, this cell method, is quite powerful because it means, yeah, great. So, well, it's slow, but it means that we can take slices of the data that we're working with and then do stuff with the slices of them. And Xarray has this slice, I guess, subroutine connected with cell where you can do that. And let's go from 0 to pi. And then let's plot to see what happened. And slice has built in this method equals nearest. So if you don't get it quite right, it's fine. So great. We just basically cut our data set in half, and we just have half of it. OK. So the next thing we're going to look at is doing basic computations. And I promise things are going to get more fireworky, but we're starting from the beginning here. So you can apply that like basic low-level NumPy operations, subtraction, addition, low-level things to Xarray objects. So we could say DA, let's make a new Xarray data array where we raise our data array to the power of 2 and then add 1. And so now we've created a new object, DA underscore G. Let's look at that. And so while that's running, what do we think would happen? What should this look like if we plot this out, the new data array?
Parabola?
Totally. So if we're looking at just this half, we squared it and added 1. So the places where it's 0, nothing's going to happen, right? Except it's going to be at 1, and it should be bigger. So we should have translated it up, and it should have higher amplitude, exactly.
So when we square f, so basically we're using the previous function, and we're like kind of squaring it, the previous function there?
Yeah, exactly. So we had DA underscore F. DA is just, and we said square that, square the data, square the values in that, and then add 1 to them. So we're starting from 1, and we're going up to almost 2, and then back down to 1. And if we plot that, but notice that the coordinates didn't change. x is still the same x. We're not squaring the coordinates. We're just squaring the values.
Basically, the sinus, we're squaring the sinus function, right? Previously.
Exactly. Totally.
Is this also like NumPy where it's actually like being run in C and then converted?
Yes. Yep. Xarray wraps NumPy.
Okay.
Yep. So it's just like invoking NumPy. Yeah, cool. So we're starting at 1, we're going to 2. Small exercise for us. If we wanted to multiply these, now we have 2 data arrays, multiply them together and select the range between -1 and 1 and then plot it, how would we do that?
So,
Oh, are you looking at the answers?
Yeah.
Oh,
well, we need a new. Well, I don't have the answers, so I'll try.
okay.
We need a new data array.
Okay,
So like DAH, I guess,
great.
and that should equal DAF times DAG, right?
Correct.
Okay, so that's step 1.
That's step 1.
Then cell
Totally.
slice. Is it -1:1?
Comma, but you're totally there. Yep.
Okay. And then dot plot.
Perfect. Nailed it. Top marks. And actually, we don't need to define. We could have it be DAH.
I was expecting this to be 3 different lines, so that's why I was going to do it step by step.
Yeah, yeah. Fair enough. Yeah, you totally could do that. Okay, great. All right, so let's play with some data. So we're going to clone a tutorial. You don't need to know what's going on here, but basically there's this website called GitHub that is a repository for a lot of code and a lot of data, mostly code. And we used a command line function to get this data. Okay, so now we have this data living in a folder called tutorial data, and in the sea surface temperature folder, subfolder, this data is from the National Oceanographic and Atmospheric Administration from a certain satellite, and it's a netcdf file.
And that's in the folder, right?
That is, that should be, yeah. So we just downloaded that data, essentially. And we could look at it, and there's our SST. The dot means starting from here, from where you are in your file tree. Dot means this file. Dot dot would be the parent folder, the parent directory. Okay. And so we know we're saying here's this data, and let's open it. Xarray.open dataset. DS dataset is just the kind of the standard way that people create objects, but you could call it whatever you want. Okay, let's get rid of that. So now we've got this real life data set. And a few things to notice. It's a data set, not a data array. And what makes a data set different, it's like the parent of the data array. A data set is wrapping a data array, and a data set has different data variables. So we've got dimensions, we've got coordinates, and we've got variables. We have dimensions of latitude, longitude, and time. And each coordinate, which is where the values of that dimension live, essentially, each coordinate has a dimension. in this case, only one. So the latitude coordinate has a latitude dimension. Longitude coordinate has a longitude dimension. But it could be the case, Moisir, that latitude could be actually two-dimensional, and it could have x and y. So it's not necessarily just because latitude coordinate has a latitude dimension, that's not necessarily true, because a coordinate could have more than one dimension. Does that make sense?
I think the way looking at this, so one thing that's really clear here is the distinction between the data set and the data array, because if you had a second variable, so you have the coordinates as kind of like the framing structure.
Yes.
That describes the unique position of every value that you have.
Mm-hmm.
And then in the variables, so you'll have whatever SST is, and then in the picture there were two things. There was like precipitation and something else.
Right.
Temperature. And so is that what SST is?
Sea surface temperature.
Sea surface
Yep.
temperature. So you have temperature as every reading of the temperature has a latitude, longitude, and time associated with it.
Yes.
And those three metadata aspects, like we can think of it in many different ways. Then there's also, not here, but presumably precipitation as well. And then you can just keep building out from that. So this is, after a fashion, you're kind of doing like a relational database where you have two tables. You have your framing unit, which has an ID with a latitude, longitude, and time. And then each ID in another table has a temperature and has a precipitation and everything else.
Yep.
So that part makes a ton of sense now, which it
Yep.
didn't earlier. How latitude, like, it may just be because I'm very hung up on the fact that the words latitude and longitude are being used, that I'm having difficulty imagining latitude as a two-dimensional anything. But so
Sure.
it is what it is.
It is what it is. Totally.
This is similar at all to like OLAP, like online analytical processing, the way they have like the cube structure of like you have at one point like the slice of that kind of that all the data shares in terms of having this like one larger like metadata, but within those then you subdivide them into categories that have like their individual relationship to a larger cube. I don't know, maybe it's a database structure, but that's a similar thing where it's like along this axis they all share this same like attribute, but like are all in themselves like individually contained data.
Yes. Yes. Yep. That sounds similar. Nice. Okay. So let's start playing with this. So we have this data set, which, as Moisir points out, currently has sea surface temperature, but could have precipitation, could have any number of data variables. So let's take out sea surface temperature only. So we can say SST equals ds SST. We could also do SST equals ds SST. It's exactly the same. And if we now look at SST, we've taken the variable out of the data set, and when you do that, what you have is a data array. So there's our data array. It has a name, SST. It still has the coordinates and the dimensions, and it has a bunch of attributes that don't do anything to the computation, but are helpful to the human that's trying to understand what it is. Okay. So now indexing, which we were doing before, like finding the fifth element, starts to become more useful, because we can say sst.cell, this is what we did before, time equals, and let's look at our time is in these date time variables. So let's say time equals 1960 06 15 dot plot. And we will give it two arguments, v min, so the lowest value in the color axis is going to be -2. V max, the highest value, is going to be 30. And so under the hood, it's using matplotlib, the basic Python plotting library, and it's showing us the data. We have a color bar, and we're going from -2 to 30 on the color bar. And we've selected this time, 1960, June 15th. Yeah.
I'm blown away by how much metadata is held inside the Xarray. Like, you know, this degree north, degree east, like, you know, that it knows to generate this kind of plot when you just run dot plot.
So I agree. Crucially, that metadata is associated with the data set. So if we look at sst.lat and look at that coordinate, we're getting that much information because it has units associated with it. So it's saying, what are the units? Latitude, units are degrees north. But yes, it's very powerful. And actually, like the cutting edge of Xarray right now is adding it with a Python unit library so that if you have a data array in meters and a data array in seconds and multiply them, what comes out is meters per second, which is just like mind-boggling. Anyway, okay, so we selected only along the time axis, but let's select along a different axis. DSS longitude equals 180. Transpose plot. And we don't have to do the transpose. That's just switching the axes, which one is on X and which one is on Y. We could also say, let's choose.
Wait, so what this is showing is the temperature over time at a specific longitude at all latitudes.
That's right.
So that's why you did the transpose, so that it still looks a little bit like a map. If we imagine a like line in the globe, well, I'm not saying this is why you did it, but this is one of the payoffs, is that if you imagine like a line on the globe and then like the Earth spinning through it over the course of a year or whatever,
yes,
then this is the streak, the smudge it leaves behind.
Exactly.
Good.
Exactly.
You just do like 45 or something, just because like this is the one that, like a line that runs completely through the ocean. So I'd just be curious what it looks like for like
Of
a
course.
longitude that like runs through way more.
Of course. And so learning point, why did this break?
Because it's not a direct degree as in set, and they have 46.
Yes. Yes. Excellent. Excellent.
Yeah, that's what I thought.
Mm-hmm. So we're over land. This is only an ocean data set.
Yeah. That's why it represents the land masses so well, even though it's not recording anything. It's because the absence directly correlates to.
Mm-hmm.
Exactly. Exactly. Yep. Totally. We could also just look at a time series at a single point. We could say ln equals 180, lat equals 40, dot plot. And we would see
Dimension reduction, so it should just be a line.
exactly. It should just be a line. Mm-hmm. And this is cool enough. We'll let that work. But we can also do operations on, exactly, so it's a line. So sea surface temperature versus time. And it's telling us we are at latitude 40, longitude 80, 180.
Within the date metadata, does it recognize a month and the year as a within a, because I guess you could just run the datetime object. So like if you wanted to, like, you had a data set where, let's say, it does it every 3 months just because it's an interval, like could you say like select only like the 3rd and 9th months of a year? So like, yeah. Okay.
We may get there.
Yeah.
We can do all sorts of, because this data set happens to be it's a date time, you can do all sorts of fun things with it. Yep. So we've got this data with a whole bunch of metadata. We can do a bunch of operations to it. We can take means, standard deviations. We could take the mean over all dimensions, which is what happens if you don't give it any arguments. So that's saying over latitude and longitude and time, just take the mean of the entire data set. That's fine, but maybe, so it turns out the mean of sea surface temperature everywhere is 13.6, but maybe we want to take the mean only of a certain dimension. So then we could say SST time mean equals SST dot mean dim equals time. Oops. And then let's plot this.
Is that just June?
Um,
Or no, it's the. I'll be quiet.
no, this is great. This is like the fun part of science, is trying to figure out like what is going to happen when we look at this.
From -2 to 30.
That's basically because we just want our color bar to saturate at both ends. So we could say from -100 to 100, it just would be, then the color scale wouldn't be very informative because we'd be looking at a very narrow range of the color scale. So the -2 to 30 is just because this is in Celsius and sea surface temperature doesn't get above 30 or below -2, really.
Is your, just question, kind of, is your focus in like climate science or anything in this area, or because I just like in that CDF, like is it normal to treat like where there isn't a geographic data held? Is it normal to treat it as a null, or how does that work? Like for example, if we were to take the mean on the longitude,
Yeah.
or I guess the latitude for that matter, like because obviously the mean is divided by like the total number of things, like would some of the categories be skewed, or would it like be able to skip over and say like the point in like Asia, for example, like half of that longitude is missing? Would it still come out the generally more thing, or would it like kind of break?
Good question. So Xarray, if you had zeros there, it would treat those as real values. But what we have in those places, let's take a look at this. We can say dot values. What we have are nans, not a number.
Yeah.
And it ignores nans. So see all these nans? It doesn't count those in the mean, which is helpful, for sure. Okay. We could also take a zonal mean. We could say, let's save the time. We could say zonal mean, and instead of time, let's take the mean along the long dimension. And we want to transpose to get the x to be time. Let's run that. Perfect. So we get a zonal mean. And you could do the same, but along multiple dimensions. So basically, however, Xarray will allow you to do use any combinations of dimensions, and we don't want to do that. I wanted to do.
Does that have to be a list?
It does have to be a list. Yep, exactly. Yeah, and I think it could be a tuple also, but it doesn't matter. Great, so now we have the mean sea surface temperature by latitude. So we've taken a line down the globe and taken the mean in time. Okay, and this is just a cosmetic fun thing, but you can specify which axes should be which, if you wanted to flip it. Okay, great. So we can also start to do other things. Actually, let me pause before we keep going. Is this making sense? How are you doing?
Slowly getting.
Drinking from the fire hose?
Yeah.
Yep, totally. Please keep asking questions. It's not like this is a 200-person lecture hall.
Yeah, so far I understand it.
Cool. Okay.
I think I also understand why the mean of dimension time is not just June.
Cheers. but yeah, the median of time would be June, conceptually.
Well, but when you do mean dim equals time, what you're saying is throw out time and replace and map just latitude and longitude, and instead of and represent time like the color there by the mean of the temperature at every point in time. I'm saying that so terribly.
I think, but you're thinking about it the right way.
Yeah.
If we had a three-dimensional, if the data is in 3 dimensions and we had latitude, longitude, and time, it'd be like smushing the data down and taking the average smushed.
Yeah, like if we imagine every coordinate has a latitude and longitude, so we imagine every coordinate has, this is tricky. I'm just imagining like little strings like going like this as they go up. But if they are actually going like this, then they're moving on the x and y plane, which can't be the case because the coordinate stays fixed.
Mm-hmm.
It's so it's not a string going up and down or wiggling its way up. It's just a ball bouncing up and down basically.
Or it's a
going
colored
up.
string that gets warmer and cooler based on how hot it is or something. Yep. Mm-hmm. Exactly. So so we gave it latitude and longitude, but Xarray doesn't know anything about latitude and longitude. Those are just coordinates. It could be anything. And in our case, if we take the mean using latitude and longitude, and it's just square coordinates, a box that is 1 degree latitude longitude at the equator is bigger than a box that is 1 degree latitude and longitude at the pole, right? Because they're coming down. It's a beach ball. They're coming down. So right at the pole, a latitude latitude, you can, if you're standing at the South Pole, you can walk in a circle and go 360 degrees of longitude, whereas it would take, 10,000 miles to walk the same amount around the. So we need to do a little bit of math if we actually want to do work on a sphere. So a change in area equals the radius of the Earth times the spacing in the points of latitude times the spacing in the points of longitude times the cosine of the latitude. And it's not, the point of this meetup is not to necessarily dig into this. It's to look at how Xarray can deal with this sort of problem. But we're going to give it the radius of the Earth, which is 3.7 times 10 to the 6 meters. We're going to transform 1 degree into radians. We're going to do the same thing for latitude. We're going to do the same thing for longitude. And then we're going to just translate this formula into code. So we're going to say r squared times d whatever sigma? That's not sigma. Phi. Thank you. Times d theta lambda. Crashing out over here. Times cosine of, and we have to convert to radians, latitude. So there's our latitude, ds.lat. And let's look at it. Make sure we got everything right. I think we did. Great. So what this is telling us is that the area, this is 1e10, the area of latitude gets bigger as you move towards the equator and smaller as you get towards the poles. So it's the area of a 1 degree box is 0 at the poles, and it becomes very large, 1 times 10 to the 10, 1.2 times 10 to the 10 meters at the equator.
Can differential geometry just be expressed through like matrices?
Yeah. Under the hood, there is a matrix here.
You're just mapping the point onto like a different thing and then showing the way that the spaces between them like grow or shrink.
Yeah.
Right? Yeah. So you just, that's interesting. Because what you're doing is in a distortion, as like in a projection of like one shape onto a different plane. You're just remapping, and that's what a matrix can do. Okay.
Yep. It's true. Yep. So we can do some things with this. We have this data array now that has one dimension, latitude, and we can say we want the area, this area, only where SST, and let's remember what SST looks like. So if we say SST 0, that's taking the first value along the time dimension. So we're saying 1960 latitude, longitude. We want, and it doesn't really matter what number we put here, because what we want to say is anywhere that this is not 0, or is not null, so it's not nans. And so that's going to allow us to now look at, let's take this, what we've just calculated, which is the pixel area, and make a plot of it. So at the poles, latitude is 0, and at the equator, the value of a pixel is 1 times 10 to the 1.2 times 10 to the 10. These are just like showing you some of the ways that like being able to do basic computations with Xarray starts to become kind of cool. So we could say, now that we have this pixel area variable, let's take the sum of this pixel area along latitude and longitude. So that gives us the total ocean area. So we're summing over this entire latitude and longitude. And then we're going to take our SST variable, sea surface temperature, and multiply it by the pixel area. And then take the sum. And we want actually that again. So let's just copy that in. And we need one more parentheses because we're going, we need to close that parentheses. Oh no, we're fine. And we're going to divide that by the total ocean area. So we've said multiply sea surface temperature by pixel area, take the sum over latitude and longitude, and divide by the ocean area. And so that gives us a weighted mean of sea surface temperature, which is different than it was before. Remember before we had this pretty smooth curve, right? If we just took a latitudinal transect. But part of what we were seeing when we were doing that was just that was just a figment of different pixel area size. So we've corrected for that, and now we see that in fact it's changing. Okay.
So
Yes. I'm going to start running this because we have to. It's going to take a second. Yes.
So it's bimodal because there are 2 hemispheres?
So, sorry. I think I described that wrong. We have time on the x-axis. So what this is showing us is that the weighted average for the whole globe is changing through time, and we have peaks at.
Yeah, that's.
Yeah.
So we have 2 peaks because we have 2 summers,
Exactly.
and the one summer is going to be much bigger because one hemisphere has more water.
Because the Earth is tipped. So the Earth is getting more sunlight in one hemisphere than the other hemisphere in summer.
But well, that explains how summer happens. But I'm curious as to why there's a distinction between the two summers. Well, I guess 1960-09, so that's going to be the tail end of northern hemisphere summer. So the average temperature of the water is hotter during northern hemisphere summer than during southern hemisphere summer.
Yes. Yes.
Why that is not super clear to me.
Yeah. So let's see.
But you may not like that. I thought it might be the other way around, because if I had to guess, I would guess that there's a whole lot more water on the southern hemisphere, or maybe that is why it is. I don't know.
So here's the sun. Totally right. Northern hemisphere is pointed towards the sun in summer. In winter, or for the other summer, or yeah, I think it has to do with obliquity.
Okay.
But it could also be that the way ocean circulation works, water that is quite cold upwells in the Southern Ocean. So the northern hemisphere is absorbing a lot of heat that then, so hot here, water that's upwelling is quite cold, so it could just be a product of that. But yes, these are great questions.
Like the data set is blowing my mind. I know I'm saying that Xarray is not fascinating, but the data set is blowing my mind.
I know.
Quite a bit more.
That's great.
Looking like having to restructure a lot of things right now. This is very interesting information.
I'm so glad.
Send us over to ProSci.
Sounds good. So, once this loads, we're going to, so basically what we've been doing so far is plotting with this like basic Platte-Xarray projection, which really wreaks havoc on the northern and southern poles. Kind of rubbish. So what we're going to do, and actually since nobody's actually typing along with me, I'm just going to copy paste this. We're going to use a different projection, interrupted good Hamalus sign, which preserves a lot more of the continental area at the expense of not having a.
So building the matplotlib is already all the different projection types, like Mercator.
So, good question.
Sorry, this is not.
This is Cartopy.
Sorry. Okay.
Yep. So Xarray has matplotlib under the hood, and it works well with Cartopy, but you have to do a little bit of you have to pass it. CCRS is Cartopy. You have to pass it information from Cartopy. And we shouldn't go into the distinction between projections and transformations, but basically, I guess I am going into it. When you plot a figure, you're saying here the projection that the figure is in is one thing, and then, but what is the transformation of the data? It tends to be Platte-Xarray. So if you ever end up doing that and run into problems, email me, and I can help you with it. Anyway, one of the big reasons that people care about Xarray is big data. Like, how do you deal with terabytes and terabytes of data? You don't want to download it and work with it locally, but you do want a way of efficiently loading it all in. So this function, openMFDataset, is one of the keys, because you can open with this wildcard, load 100 files in and combine them by coordinates or by a dimension. And remember how we had SST. If we go look at SST, we see a bunch of different files. So OpenMF dataset is going to open all the files and combine them into one dataset. And it hasn't loaded all of it into memory. It's lazy. So it has basically like arrows pointing to the data, but it's not going to break your computer because it's using Dask under the hood.
Which, if you were part of Data Club last year,
you would have come across it. Deep cut.
Wasn't that like the last thing that was
One of them,
last
yeah.
meetings?
DSSST. Okay. We have 7 minutes. Do I want to jump into doing group by? Sure. Let's do it. So group by is a very powerful way of playing with data. Basically, imagine you have different grapes and you want to say, I want only the broken grapes. You can say group by broken or not broken, and then take the mean of the broken grapes, and then combine them at the end. That is my analogy of the day. So what we're going to do here is we're going to say DSSST dot group by time month dot mean dim equals time. And so we're grouping sea surface temperature by time and then taking the mean by month, and then taking the mean along the time dimension. And so we've reduced it to, before we had years, and now we just have we've split it into a, basically climatology is what they would call it. And if we then plot that, SST, climatology, let's take the 6th month minus the 0th month. Boop.
so this is May minus January?
Yeah, this is wrong. Yeah. Mm-hmm. Exactly.
So northern hemisphere gets hotter because summer's happening.
Exactly.
Southern hemisphere gets colder.
Because it's winter.
Well, winter is coming.
Yeah. Mm-hmm.
Nice.
There are a whole bunch of, yes.
It's mean over the years, yeah? So
Mm-hmm.
the entire period.
Mm-hmm.
So it's average June temperature minus average July temperature at every point. Yeah.
So we said, let's split up the data and stack it by month, and then take the mean by month, and this is what we're left with. So now we've changed it to just changed the time dimension to only being by month. Exactly what you just said. Okay. Maybe last thing, or almost last thing, we can resample. I think this is getting to something that you were asking. We can resample data and take a rolling mean, do all of these. Ln equals 300, lat equals 10, just for kicks. So we have this seasonal cycle. We've taken 1 point on the globe. Seasonal cycle is dominant, as you could imagine.
There's just some interesting analyses. Like, I mean, this is something that people have done a dime a dozen, thousand times over. But just like all the different averages and like trends, you could like start to like come. I'm an undergrad, so like I'm just like seeing the fruits of what this stuff could do.
Totally. It's very exciting. And especially, I mean, the data is very exciting.
Yeah.
And I agree that Xarray doesn't seem as exciting, but the fact that it is this easy to do ask these sorts of questions is because of all the architecture that Xarray has. So it's not just a blank three-dimensional matrix that you have to sort of like MacGyver. Okay, so we've hit 6. I wish I could just keep going.
Well, let's call it, and then yeah, be excited.
Be excited. If you have more time and you want to look at these things, where we're getting, and actually I'm just going to, oh, I can't do that. There is, we have, basically this notebook goes through group by in detail, and talks about different ways of taking rolling means and coarsening data. And then we get into a more real-world example of like splitting up the ocean into different basins, and looking at sea surface temperature by different basins. And then there's an exercise to calculate the El Nino index, which is something that one often has to do in oceanography. Basically, you take this band, you snip out a band from the Pacific Ocean and take, and the index is 5 consecutive 3-month running mean of sea surface temperature anomalies. So you have to remove the seasonal cycle from sea surface temperature and then do these transformations, and then you get the El Nino index, which is pretty darn cool. And then there's NOAA, the National Oceanographic and Atmospheric Administration's actual El Nino index that you can compare it to. So that concludes our first meeting. Do y'all have any questions?